Hello and welcome to a video on my latest piece of test equipment, a Panasonic VP-5610P oscilloscope. Now, I've been meaning to get an analog scope for quite a while now, but I've never come across something that I really felt I absolutely needed to have until I found this particular oscilloscope. Now, as you can see, this looks like a perfectly normal analog oscilloscope. It's got plenty of features. It has, for example, a delayed time base. It's got the alphanumeric readout on the CRT. It actually has a third channel as well. The controls for that and the input are on the right hand side. But the reason why I absolutely fell in love with this oscilloscope is its size. As you can see here, it is a very compact unit, especially for the kinds of features that it packs. Now, there are obviously smaller analog oscilloscopes than this, but most of the ones that I know of are fairly limited when it comes to features. So they might only have one channel or maybe two, but certainly not three. And they definitely wouldn't have things like a delayed time base or a readout on the CRT. So I think from a feature point of view, this model is pretty unique in terms of what features it packs into a very compact form factor. Although I must admit it is actually fairly deep, so it's actually only really the front panel that is nice and compact. And to be honest, the whole front panel looks fairly snazzy as well. You've got those lit buttons here, and it just sort of has this sort of nice mid-80s vibe to it. So it's also very nice from an aesthetic point of view, for me at least. But what made me buy this particular instrument here is one of the accessories that came with it. So if you just give me a moment, I'll set it up and show you. This here is an external DC power supply that can power the oscilloscope of either a DC voltage or a built-in lead-acid battery. Now, this external power supply is about as big and a few times as heavy as the oscilloscope, and if you look at the label on here, it can run the oscilloscope for about an hour off the internal battery, and it takes over 8 hours to fully charge the battery. And I think this is absolutely amazing just from a historical point of view, that you have this massive box which will power your analog scope for an hour. Now, unfortunately, this thing doesn't work at the moment. I highly suspect that the internal battery is flat because the charge light doesn't come up when I turn it on. So I think what we should do is we should have a look inside this box first and see if we can get the battery working. So this is the inside of the power supply, and there's just an awful lot of stuff going on. There's inductors and capacitors and through-hole components and wires everywhere, and you've got a whole bunch of power semiconductors mounted to the bottom plate of the instrument, and yeah, lots of things going on. Part of this circuit will be the battery charger for the battery here, and another part will be some sort of step-up converter, because the way the scope is powered is through this IC connector here. So the idea is that the scope sits on top here, and this plugs on the back of the scope in its main socket. And so presumably something in here steps the battery voltage back up to something that the scope will be happy with at its mains input. This battery here looks suspiciously like a 12 volt 7 amp hour sealed lead acid battery. So I'll just get rid of the cover and we can have a look inside and see if that is correct. As expected, the battery here is indeed a 7 amp hour 12 volt sealed lead acid battery, and this is really good news because this type of battery is extremely common. They're commonly used in things like alarm panels and backup power supplies, and this means that replacements are readily available. So readily in fact that I happen to have a replacement right here. I may have prepared that one in advance. So I think what I should do is just quickly have a look at what the output of this battery is to see if it is indeed flat, but I highly suspect it is, and then chuck in the new battery and see if this whole thing springs to life. Now, before I go and change the battery, I would just like to draw your attention to this very interesting label on top of the battery cover here. This label talks about basically safe settings of the front panel switches while changing the battery. The obvious problem with this kind of instrument is that it is able to generate a reasonably high voltage for the oscilloscope to run from. And if you've got your front panel set so that it will be turned on, but change the battery, the instant you put your new battery in, this circuit will spring to life and will have exposed high voltage all over the place. And obviously then if you touch the wrong pieces, you might just as well electrocute yourself. And it's just really interesting because it shows what was considered user serviceable 30 years ago, and what kind of expectations people had of the common sense and intelligence of the users. So first of all, you have to get through no less than 10 screws to get the car off in the first place, and then you're sort of expected to follow those instructions and don't touch things you're not supposed to touch, and all of those things. And presumably people didn't kill themselves while changing batteries in those power supplies. And I'm just sort of trying to imagine how would this be designed today with today's safety standards. I mean, presumably you wouldn't take the cover off at all. Presumably there would be a battery pack which would be completely sealed, and there would probably be some sort of microchip in there to keep track of the battery and everything. So it's really just very interesting to see how certain things have changed in not that much time, and how our perception about manufacturers' obligations on safety have changed as well. So really interesting, this one. Okay, the new battery is inside the power supply, and let's see if this puppy can actually power the oscilloscope. So let's switch this to power supply mode and internal battery, and ooh, lights are coming on, that looks good. And let's turn on the scope. Ooh, yes, the scope is running from our little battery. This is extremely exciting because now I have a extremely portable battery-powered analog oscilloscope, and I'm very happy about that. And before we look at the oscilloscope itself, let's just have a quick look also at how the power supply connects to the oscilloscope, because I think there are a few quite neat little tricks that they played when designing this tandem unit. Now, the way that the oscilloscope attaches mechanically to the power supply is quite interesting, I think, because it allows you to use both of them together as an integral unit, or just the oscilloscope itself as a normal Benchtop scope without any modifications. Now, if you have a look here, the oscilloscope only has front rubber feet, and these align with those metal humps on the power supply, so the feet have little indentions and they come down like this and align. And they're kept captive so they don't move around too much. The power supply on its back has those little pillars here on which the oscilloscope just sits, and there is a little threaded hole on the bottom of the oscilloscope. And if you just sit on top here, it just sits quite securely already. Now, what you can do as well is, if you want to screw them together, there are hollow pillars going through the power supply here and here, and there are captive screws inside the power supply. So if you go on the bottom of the power supply, you can tighten those screws into the oscilloscope, and the scope and the power supply will be held together very securely. If you want to use the oscilloscope as a benchtop instrument, all you have to do is just take it off, and it will just rest on its rubber feet on the front, and on the back it will actually rest on this bumper here, which is on the same height as the foot here. So you don't have to take off any feet or modify it in any way to change between being attached to the power supply or being a benchtop instrument. And this idea continues on the back of the instrument. As I said before, the output of the power supply is through this normal mains cable here, which plugs into the mains input of the oscilloscope, so you don't have to faff around with a extra DC input or DC power supply for the oscilloscope. It just works through the normal mains input, and if you want to run it off mains, you just plug your normal mains cable in there, which again means minimal changes required. And also the back feet of the oscilloscope and the back feet of the power supply are in the same plane. So if this is screwed together as one unit, you can just stand on its back and use it on the floor if you so desire. And also the carrying handle will carry both instruments as well. So I think in this particular case, the idea of having an external battery pack or DC power supply for the oscilloscope has been really well executed. It looks to be very well thought out. Obviously from today's point of view, the practicality is somewhat dubious, but I really like the oscilloscope and the power supply, just the way it works together, and I think it's a bit of a curiosity if nothing else. In order to have a look at how the power supply and the oscilloscope work together, I've got this multimeter here connected to the output of the power supply, and also the oscilloscope to the output of the power supply, but that is going through the power meter here. So down here we can read the current and the power that the oscilloscope actually takes. So first of all, I'll turn the power supply on, and we can see immediately that we're getting 143 volts out of the power supply. Now this doesn't show up on the power meter, but it does show on the multimeter here. This is actually DC voltage. So right away we can tell that this power supply isn't generating AC for the AC input of the oscilloscope, but rather DC. And we'll get back to that in a moment. But it's 140 volts, and now we turn the oscilloscope on. And we can see that the oscilloscope is drawing 37-ish watts, and that the voltage dropped to 112 volts. If you look at the back of the oscilloscope, it is rated to operate from 90 volt AC to 250 volt AC or something like that. And if you look at the 140 volt DC, that would have actually be compatible with, say, around 100 volt AC, because the 140 would just be the rectified mains voltage. Now 100 volt DC is actually quite low, so what this tells us is that the power supply in here can actually operate from a very wide range of voltage, so all the way from just over 100 volt DC all the way to 250 volt AC, which would be a peak voltage of well over 300 volts. So I'm sure they did some really good design in the power supply in there. What we can also immediately tell by the oscilloscope working off a DC voltage on the AC input is that it must have a switched on power supply inside, because if there was a transformer, then, well, that wouldn't do anything at all if it was fed with DC. And in principle you could run any switched on power supply that's made to run off an AC voltage off a DC voltage. However, there are a few catches you need to be aware of when you design the power supply, and those are ones that Panasonic must have been aware of when they made the power supply for this particular oscilloscope here. So just to explain this point a bit better, let's just have a quick look what you would normally expect to find inside a AC switched on power supply, and why it can run in fact off DC, and what the catches you might find might be. So in principle what you have is your AC input here. You will find some sort of rectifier, a very large reservoir capacitor, and then the actual switched mode power supply, which outputs your output voltage or voltages. And the idea is very simple. You've got your incoming mains voltage, which is AC. That gets rectified and smoothed here. So at this point you will actually find a DC voltage with, you know, some sort of ripple on it. And then the actual power supply itself, which is just this sort of black box here, will convert that DC voltage to your output voltage here. And you can see immediately from this diagram that it shouldn't be a problem at all to run this kind of power supply off DC, as long as the voltage at this point is within the range that this converter here expects. One of the problems you might encounter though is the power dissipation in the rectifier, and that's true for both single diodes here or a bridge rectifier. If you run the input of AC, this diode will only carry current for one half-wave cycle. Similarly, in a bridge rectifier, each diode pair will only carry current during a half-wave cycle. But if you run the power supply of DC, the diode will actually carry current for the entire time, and so you will dissipate more power in the rectifier. And if the rectifier hasn't been designed to cope with that increased power, then you might burn it out. Now, another problem you might run into are fuses. Normally you would find some sort of fuse in the power supply, and this fuse will normally be rated for an AC current. The problem is that fuses that are rated for, say, 250 volt AC and a few amps might actually not be capable of breaking the same kind of DC current, because DC currents are much more prone to creating arcs inside the fuse, and so your normal little glass type fuse might not be capable there. so you need to be aware that you might no longer have the overcurrent protection from the fuse. And finally, our simplified model obviously assumed that this DC-DC converter is very simple and there is nothing else around here. Obviously you have things like active power factor correction, or this converter here could look at the actual input frequency to make sure it's within specifications. So if there's anything in here or in the front here that relies on there being an AC input, then obviously this whole thing won't work off DC at all. But as I said, in principle you could run most AC switch mode converters off DC if you're aware of the issues you might encounter. Now, just another interesting side note, as you can see the oscilloscope is currently drawing 37 watts. I'll just quickly turn off the light so we can see it better. Now watch what happens when I turn on the scale illumination of the oscilloscope. The power went up to 39 watts, so just illuminating the graticules on the screen takes about 2 more watts from the mains, which is just amazing. So I think before we get to the more interesting business of taking the oscilloscope apart, we should have a brief look at the manual as well, because it is quite interesting. In this general section here, it talks about the input voltage range of the power supply, and there is this interesting sentence here which states that DC operation is optionally available. Now, I presume that this doesn't refer to the normal power supply accepting DC inputs at a certain rate, but I presume that this means that you can actually swap out the entire power supply module for a DC power supply, so you could run it off, say, 48 volts or 12 volts or something like that. So that's quite interesting, I think. Next up, we have a table of accessories that came with the oscilloscope originally. And the interesting one here is that it does come with a spare scale lamp, so if that should burn out you can just replace the lamps yourself. So clearly they designed that in so people could help themselves. And it also comes with a power cord, and later on there are diagrams of the different power cords that are supplied. So for example, you've got the US style, EU style, Australian, and then this one here is for the UK, because back in those days appliances didn't usually come with plugs fitted, so you had to fit your own plugs to the wire ends on a UK appliance. And I think that's really quite interesting because you know, nowadays health and safety people will probably get heart attacks at the mere suggestion of people fitting their own plugs to their appliances, so I really like this one. So this section here is also quite interesting because it talks about battery replacement. The oscilloscope has a built-in 3-volt lithium battery for memory backup, and they give it a lifetime of about 3 years, after which you have to replace it. They do suggest to talk to your local Panasonic representative for changing it, but it does seem to be, well, maybe user replaceable. But at any point it would be quite interesting to just see how the battery has fared over the last 30 years, or if it has been replaced at all in this time. And this page here is just a pure gem. It talks about how the internal microprocessor may occasionally crash, and it tells you what to do to basically reset it. And I think it's quite nice of them to basically include this page and admit that yes, we know our firmware may crash, here's how to fix it. Whereas today most manufacturers would be quite reluctant, I believe, to admit that their software may be anything but flawless. Obviously everybody knows that software still crashes occasionally, but just getting this sort of heads up from a manufacturer is quite a nice touch, I believe. Well, the cover came off the oscilloscope easy enough, and this is what's inside viewed from the top. Over here we have the CRT, which is probably the reason why the whole thing is so long. Next to it is the high voltage power supply. And you've got 2 cards here which are full of digital chips, so presumably that contains the microprocessor and whatever else is needed to control the instrument. Over here, this card is presumably the channel 3 vertical amplifier, I would guess. This little board here might be controlling the fan or something due to its position. And on the back here we have the power supply, which appears to be a separate unit which could potentially be taken off and replaced with something else. So we'll look at that at a later point as well. On this side here we have what appears to be the output amplifiers for the CRT. So this here is the no touchy zone, and these transistors here and those mounted here on the heatsinks are presumably what actually drives the deflection plates. And the best part is on the bottom, which seems to be, well, I don't know what it is. It looks like it came out of some 70s hi-fi equipment. Well, I guess it must be the time base and the channel 1 and 2 input amplifiers and probably the trigger circuitry and that sort of business, but it really looks extremely, well, messy in a way. You've got wires going everywhere. You've got like these green wires here, just jumpers going from this end of the board to that end. You've got a little daughter board tacked on, and you've got those, well, not really hybrids, but extra little boards mounted everywhere, and tons of trimmers, and yeah, well, I mean, I don't know what is what on there because it's not really obvious. I mean, my guess is that over here and over here you've got the 2 channel input amplifiers, and I would guess that this might be the time base. I mean, there are some markings on the silk screen, but it's not entirely clear from that. But yeah, it really looks like it comes out of some sort of, well, 70s Japanese hi-fi equipment and not a oscilloscope, but I guess that's how they built stuff back then. Yeah, really fascinating. I'll put some more high-res photos up on the website later on if you want to have a closer look. So just to show you a little detail here on this board, you've got this capacitor here, which is tacked onto the leads of this chip, and its leads are in this sort of nice heat shrink. I'm not sure if that was an afterthought or if they couldn't fit it on the board, because I mean the board is fairly densely populated. Obviously you can see through the way the traces are done, these boards are clearly laid out by hand without CAD, and yeah, I mean it's just really cramped in there and just lots of stuff going on. I'm wondering how many people they had working on this design. And it seems we are having an actual botch on the CRT driver board. You can see here we have 3 trimmer caps, and there is a footprint for another one next to those 3. However, instead of a trimmer cap, we have this nice arrangement of components here. So you've got the ceramic capacitor, which has one of its legs stuck in the air, and then there's a resistor going from that leg down to a pad and another resistor across it, and you've got this electrolytic capacitor down there across here where the other ones have ceramic caps. So this must have clearly been an afterthought where they decided that they'd much rather have this arrangement of components instead of a trimmer cap in this place on the board, and well, it seems to be doing its job. And over here we also have a capacitor that was fitted in between other components, and their legs lifted up in the air as well, so I presume they were fine-tuning the frequency response of the whole thing, or maybe even the stability there, which is, you know, quite nice, I think. And down here it appears we have 2 surface mount components, which is really interesting because everything else in here appears to be through holes, so they're labeled CR, so presumably diodes or something of some description. Really interesting. I think next I'll take out those 2 digital boards just to see what's on there. I'll probably leave that board in because there's just a whole lot of wires and cables going everywhere from it, so I'm not entirely sure if I could fit it together again afterwards. Interestingly, there is this sort of empty space here which does have, well, there's some unpopulated footprints for more connectors down here, but it also seems that you could fit another card here. Presumably that is for the GPIB connector that you could fit here, so that might be an option. But I'm really curious how they actually fit that in, because there isn't a whole lot of space between the case edge and this card, so I'm wondering what kind of connector they have and how they actually wire up that connector to presumably this card. So if anyone has the GPIB option for this scope, please let me know how it looks like, because I would be more than curious. Okay, so here we have those two digital cards. Very helpfully, they did actually label them for us. This one here says CPU board, and this one here says character. Presumably that's the alphanumeric character generation for the readout on the CRT. And again, these cards, they just have those little details on there which just have, I'm not sure if they're bodges or actually designed this way. So let's take, for instance, I mean, here you've got, again, resistors running between places. There's a resistor between those two pins here. I mean, there's a whole bunch of, I mean, this must be a bodge wire on the back, obviously, but you know, these resistors, were they designed or bodges? I don't know. And on this board as well, there's a few little details all over the place. I mean, one thing that's also very curious is the way these connectors are mounted. So the boards sit in the cage like this, and the connectors come in from the top. And they're just all over the board. So you've got one's going this way and one's going that way, and they're standing off quite a large amount. So yeah, it's really interesting. And you see this backup battery here is mounted on top of all the ICs with its legs going down. So it just, I'm not saying it's bad engineering, but it just seems, well, it just looks a whole lot like, yeah, they did bits and pieces and then tried to fit them in the case, and yeah, but it's very fascinating, I must admit. One thing I would like to do is measure the backup battery, because I'm really curious how this has fared over the last 30 years. And what I'll also do later is I'll just read out those two EPROMs, and I'll also put the files on my website later, because I don't trust those, well, UV window EPROMs for keeping their data much more than 30 years in the first place. So I'll be back in a moment with the multimeter. Okay, so let's have a look at this battery. Now let me just see if I can get the probes on. One here and one there, and we have 3.3 volts. Which is very interesting, considering this thing is 30 years old. The battery type is a BR2325. Now the BR is just a slightly different chemistry from your regular CR type coin cells, which have a lower self-discharge, but still 30 years seems an awful long time, and even having 3.3 volts seems pretty high. Now I'm just trying to work out whether this battery has actually been changed at all. One battery pin is here and the other one is over there underneath this resistor, and there doesn't seem to be any sort of fluxes around them, so they might still be the original solder joints. They are slightly more shiny than all the other joints, but so are those bodge resistor joints, so maybe they soldered the battery by hand at a later point and it's still the original one, which would be amazing. And here's another little detail that I just found on the character generator card. This pictogram here appears to be the 1985 Panasonic equivalent of the modern ESD warning sign, which I think is quite nice, the little finger with the ground strap. Here's just another little observation that I found quite interesting. On all of the boards, all of the chips, all the capacitors, all the connectors, as far as they are labeled, are made by Japanese brands. You've got Hitachi, you've got Toshiba, you've got NEC, you've got Matsushita, everything is there. But over here, you've got those two TL081 op-amps, which are from TI, and you've also got this one lonely 74112, which is also from TI. So it's really interesting, especially the op-amps, because, you know, TL081s aren't that special. So I'm wondering why they've gone for TI here instead for, you know, something Japanese as well. Really interesting, I think. So while we were taking a look inside the oscilloscope and all the boards, and I've been doing other things like reading out the EPROMs and everything, this power supply here has been left charging its battery, and it's probably been a few hours now. I'm very slow at making the actual videos, and it's gotten really hot. Like, even the top is fairly hot, and if I touch the bottom where the power semiconductors are, I can't actually leave my hand on, because it does actually hurt to leave my hand on there for more than a few seconds. So I'm wondering if it's supposed to be getting that hot while charging the battery, and I wonder if I should have looked inside to see what's going on. Well, maybe later. I'll just leave the paper manual on top just to get the fire started more easily, and we'll see about it later maybe. So I think we might as well have a quick look at the temperature. On the top here we have something along 30, so here on the stud it's hotter, 40 degrees here on this stud, which is, yeah, probably one of the warmest parts on the top, 42 degrees, that sort of area. And on the bottom, ow, 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 on the bottom we have, oh, hot just about here, 45, 50, 55, 56. It's probably closer to 60 to be honest, because I'm not making great contact here, but yeah. Oh, 58, 59, 60! Oh, over 60, 62, wow. Yeah, 65 in places. So yeah, 65 degrees surface temperature while charging the battery. Maybe I should have a quick look inside to see what's going on just before I burn down the place. And this is going to be the part of the video where I'm going to kill myself due to electrocution. The battery seems not too hot. There is a bit of heat coming from this sort of area, but it's a fair bit to be honest. I'm wondering if it's a good idea to poke the thermocouple on there. What could possibly go wrong? That's really where a thermal imaging camera would be quite helpful, but I suppose everything is fine. I think most of the heat is actually coming from, as I said, there's power semiconductors mounted to the bottom plate. So I think this is where all the heat is coming from, but it is just slightly worrying that there's so much heat on the outside surface as well. But yeah, I guess it's fine. It's been sitting like this for a few hours now, so I think if something was to catch fire, it would have caught fire a while ago. So I think we're safe. Unfortunately, I don't want to take the oscilloscope apart any further because all the other bits seem to be reasonably well integrated, so even the cover for the high voltage generator here is mounted with a bolt on the bottom, so I don't think I can get it out very easily at all. And also this card here has just tons of cables and wires running to and from it, and I'm not quite sure if I can get it back together just the way it is right now. One thing I still do want to look at is the power supply. I've already taken off the 4 screws on the top and bottom, and the power supply just comes out like so. So it is a self-contained unit and just connects to the oscilloscope with this little connector here, which obviously has a mating half over here on the oscilloscope. And it's actually quite interesting again because you seem to have those sort of holes here and there for presumably airflow, and these ones here match up with the back of the CRT, and these holes here match up with this inlet here where the main fan of the oscilloscope is sitting behind. So I guess they're creating some sort of air draft from the back of the CRT through the power supply and out through the fan, which is quite nice. Anyway, I just cracked the power supply itself open and have a look at what's inside there. So the insides of the power supply look like a basically very conventional switch mode power supply, at least of what you would have expected in 1985. Just looking at the components, these are basically the same sort of style of transformers and capacitors that we found in the DC power supply, so they do seem indeed to have been designed by the same kinds of people, or at least with very close collaboration. One interesting detail here, they're obviously using the case as a heatsink, so you've got tons of TO220 components mounted to the side here, this big fat presumably integrated switch mode controller mounted to the side here, And then you've got this little bend in this bracket, and you've got even more stuff mounted from behind, and I'm not sure if you can see it, but this little transistor here is mounted on the top here, and it's connected through wires that are going through the back here onto the board. So clearly they couldn't fit this any other way, which is, well, just quite neat how they went out of their way to make this bend in this bracket to fit all the components on the heat sinks. And again, all the components in here, as far as I can tell, are Japanese brands, except for the Amphenol connector here, and down here we have two Texas Instruments TL081s again. So presumably they must have struck some pretty good deals with TI for their op-amps back then. So I just put the cover back on the oscilloscope, and one last thing I would like to look at is just how easy the replacement of the scale lamps is. So for that, presumably I have to loosen two screws on the top here and the bottom here, and take off those knobs in order to get in. So let's see if that works. Okay, 4 screws and 3 knobs later, this front bezel seems quite loose, and let's take it off and see what's inside. So the first thing you'll notice is that the color of the CRT itself is actually white, and the tint, the blue tint, is just from the screen here, which is fairly normal. And you can see down here we have our 2 scale lamps, which presumably you just pull out to replace. So let's just bring the camera in a bit closer and have a more detailed look at this LED. I think you can see it better from this angle. This power LED is in fact socketed. You can take it out and replace your power LED. And it looks quite bent actually. I'm not quite sure if it's supposed to be that way. But yeah, this is absolutely adorable. I'm not quite sure why they socketed the LED. Presumably in order to make it replaceable, or maybe they didn't have a long enough leads on that. So yeah, if you're one of those people who likes to replace all of their LEDs for bright blue ones, this is the oscilloscope to get, because it seems to be pretty easy to do in here. I'm actually quite curious now how all the other LEDs on the front panel are mounted, so I might just have a quick look at those as well. So I did totally not expect that. After just undoing those 2 screws here, the entire front panel assembly just lifts out like that, and you've got access to, well, all of your front panel circuitry, which is connected through this ribbon cable. And you can see the BNC connectors are in fact separate from the front panel, so that's really quite nice. You can see here the illuminated switches on the front panel are sort of integrated chobbies, so it doesn't seem to be that easy to replace the LEDs, which is fine by me because I actually quite like the orange. See if I can fit it back together again. There we go. Now here's just one final detail that I forgot to mention earlier when looking at the manual. You'll see that the front panel BNC connectors are angled slightly downwards, and at first I thought that the oscilloscope actually got damaged during transit, and I was actually a bit annoyed about that. But then looking at the manual, it actually states here that they are mounted like this on purpose. Presumably the intention is for probes and cables to be kept away from the front panel and prevent them from interfering with you trying to operate the controls. And whilst I haven't noticed any particular improvements using those angled BNC connectors, it just shows that there was a lot of attention to detail when they designed this oscilloscope, because I certainly wouldn't have thought of angling the BNC connectors that way. So after having taken this sneaky little look inside the oscilloscope, it's on its rightful place on the equipment shelf along with this power supply here. Obviously I don't know how useful the power supply will be in practice, and I actually doubt that I will ever use it in anger, but at least I can sleep safe and sound knowing that I can use the oscilloscope should the zombie apocalypse happen. And if nothing else, it will be a very good blunt instrument to defend myself against the hordes of the undead, so that's a bonus, I suppose. Anyway, I hope you liked this video, and I also hope that you found the insides of the oscilloscope as interesting as I found them. And so yeah, thanks for watching, and I'll see you next time. Anyway, I think I'll put this back together now, and we can have a look at a few more... No, There isn't anything else. Also, the back feet of the oscilloscope and the back feet of the power supply are on the same plane. So if that is screwed together as one unit, you just can't stand it on the and the oscilloscope together, because I think there are a few little... So what I'll do, I'll just turn the power supply on, which I do this, and now I'll also turn the oscilloscope on. And it's a fail.